For the past 12 years, I have been a researcher in the field of regenerative medicine. As a doctor of neuroscience, my work investigates whether or not we can use stem cells to help children who've had brain injury or adults with spinal cord injury. Today, I am going to speak with you about how we are changing the future with stem cells. I believe that stem cells are the new internet. Think about it. Think about how the internet completely changed the way that we communicate, the way that we do business, and even the way that we gather data and information. Similarly, I believe that stem cells have the power to revolutionize the whole concept of healthcare. So to start, let's have a little audience participation. Put your hand up. How many of you have heard of the term stem cells? Now leave your hand up if you can tell me what they are. This illustrates a very important part of my work in science communications. Most of us have heard of the term stem cells, either through the media or through our friends, but very few of us actually know what they are, what they can do, and importantly, what they can't do. So today we're going to speak a little bit about what stem cells are. We're going to look at what they're currently being used for and where the future of the field lies. So you can't be expected to understand about stem cell treatments if you don't understand what stem cells are to begin with. This is something that I like to call Stem Cells 101. So we all know that the hundreds of cells in the human body all originate from one fertilized egg. If you think of this as a ball rolling down a hill, at the top of the hill, the ball can go to any number of destinations downhill. But as it rolls down, guided by gravity, it hits a series of forks in the road, after which it must make a decision to go one way or the other. And that restricts its potential outcomes. Similarly, stem cells, during the process of differentiation, face a series of fate decisions where they must choose which cell type to specialize into, and they cannot go back. Near the top of the hill, you see pluripotent stem cells. Pluri meaning many, potent, potencies. Embryonic pluripotent stem cells are the type of stem cell that people most often associate with the word. However, in reality, these cells are virtually never used in transplant paradigms. Instead, we differentiate the cell down into multipotent progenitors that are very specialized for the type of tissue that we want to get. It's important to note that one type of multipotent cell cannot make adult cells of another type. So for example, fat stem cells cannot make cells of the brain or the eye, and vice versa. So you might ask, if pluripotent stem cells can turn into any cell in the body, why don't we just inject those? You know, they could go to the site, they could travel and go to the site of whatever's injured and turn into the cells that we need. Right? Wrong. Because they could turn into something like this. This is called a teratoma. The problem is, once we put stem cells in, we cannot control where they go or what cells they turn into. They could turn into all of the cells in the body, all at once, all in the same place. Here you can see hair, fat, tooth, gut, bone. Imagine if this were in your brain or your eye. This is why we must differentiate cells into the specific progenitors as much as possible before we're thinking of transplanting them in. Now, all of our adult tissue has its own multipotent cells within it. That's what helps us to grow, or when we're repairing injury. And these can be harvested in many tissues and grown in the lab for transplanting paradigms. However, there are some tissues that you can't harvest. Think about the brain or the heart or the eye. Going in there to get cells could kill you. So we have to think of other alternative cell sources for these cells. And this is where pluripotent cells come in. Now, up until now, embryonic derived cells have been differentiated down the hill into the stem cell types that we need. Recently, induced pluripotent stem cells were developed, where you can take adult skin samples, your own consenting adult, push them back up the hill using 4 chemical factors, and then differentiate them down to the cell type you need. This was discovered recently by Shinya Yamanaka, who went on to win the Nobel Prize. The good thing about this is it uses non-embryonic sources, and it's your own tissue, so your body's not likely to reject it. Alternatively, direct lineage reprogramming, which, there we go, takes you from A to B without this intermediate step up the hill. And you can take adult skin samples and differentiate them directly into the cell type you choose using different chemical triggers. Now, this is only in the lab phases. It's very new, but it represents a very interesting direction into where the field is heading. So, what are we doing with stem cells? Here's another audience participation. How many of you are affected by or know someone who have been affected by any of these diseases? Put up your hands. Stroke, burns, diabetes, injuries to joints. Now look around. Every single one of us is affected by diseases that stem cells could potentially one day help treat. So, just because we are putting stem cells into the first person in the first trial doesn't mean that these are a treatment, doesn't mean that it's a regular accepted treatment. As you can see here, it can take up to 10 years or over to get through the clinical trials pipeline. Science is incremental. But the good news is we have a lot of treatments that have been in the pipeline for many years that are just now starting to come out. Furthermore, now, more than ever before, scientists, clinicians, members of the public, policymakers are all working together to streamline this process. That means we can get the best stem cell treatments out to the people who need them the most in the shortest amount of time. So here you see these diseases are color-coded based on where they are in the pipeline. You can see that we have 2 current treatments using stem cells here in green. The first, for bone and blood cancer, you might know of as a bone marrow transplant. Been used for decades. The next stem cell product to come out of the pipeline is for burns and wound healing. So this uses skin tissue and helps with vision burns as well. So today we're going to focus on 2 major areas that we're using stem cells in. The first is stroke. This is my work in childhood brain injury. Did you know that cerebral palsy is more common than juvenile AIDS, childhood leukemia, muscular dystrophy, and juvenile diabetes combined? Cerebral palsy, which means problems sending signals from the brain to the muscles, creating movement, is the most common neurodevelopmental disability. What my work does is we inject stem cells into the brain, which are able to incorporate and turn into the types of cells that are lost in the most common forms of brain injury. They can enhance function and restore brain tissue. And what my work in particular has been able to show is that we are able to functionally double the signal speed in the brains of animals. What could this mean for a child with cerebral palsy? This could mean the potential for normal movement, the ability to go out and run and jump and play with their friends. Very exciting stuff. Right now, these cells are being used in clinical trials only. There are trials in adults looking at stroke, and there are adult trials looking in spinal cord injury. The same cells are lost in these models. Importantly, the first clinical trial using these types of cells has now started in children. So, next, I want to focus on a very interesting area that's combining 3D bioprinting with stem cell regenerative medicine. This is in red because it is only in the early stages, but I think it represents a very exciting avenue through which the field is heading. With improvements in imaging software and technology, we are now able to make accurate 3D images and take scans of body structures inside the body. Using AutoCAD and 3D software, we are able to make CAD designs which can be printed using 3D bioprinters. Now, these bioprinters are kind of like the printers you have at home, only instead of using ink, They use special biogels to create the structures that you have in the body. Here, after that, you can seed them with stem cells. Here you see a heart valve being printed, which can then later be seeded possibly with your own stem cells. There's an image on the inset of the heart valve. There's also an image of an ear being seeded with stem cells, which can be your own. Underneath, you see a 3D printed image of a trachea, and on the bottom right, you see an interview that I recently did with CTV National News on the youngest ever transplant recipient of a trachea seeded with her own stem cells. Now, it's important to note that while this is very exciting, it is still in its infancy. We cannot make complicated structures with multiple cell types, and right now it is just very basic. But think about where this can head. Think about whether, we could use it in the future to print structures in the body and use our own cells for transplant. So, this is a very exciting field. But as with every potentially game-changing technology, there are challenges. This used to center around the use of embryonic-derived stem cells. But recently, with the advent of the induced pluripotent stem cells and direct lineage reprogramming, which can use your own adult consenting tissues, this conversation has become less and less relevant. Now, what we see, especially with the increase of treatments coming out of the pipeline, is misrepresentation of stem cell strategies. Here, some doctors are offering unproven treatments using stem cells for profit. Unproven. That means A, not proven to work, and B, not proven to be safe. Recently, Scientific American had an article about a woman who went to a very fancy clinic in Beverly Hills and got the latest stem cell facelift that they were offering. They took advantage. The doctors took advantage of a loophole in the law, sucked out her fat, and put the stem cells in her face to make her rejuvenated or healthier or something. And while they were under the hood, they gave her dermal filler. Now, what the doctors didn't take into account is that dermal filler differentiates bone stem cells, or fat stem cells into bone. Bone. And so this woman was left with bone fragments in her eyelids. This is why we need clinical trials, to make sure that treatments are safe. If you were to take a drug and you had a bad side effect, you could stop taking the drug and that side effect would go away. But it's not the case with stem cells. Once stem cells are put in, they can never be taken back out. Furthermore, going to an unregulated clinic can exclude you from future legitimate trials. So how do you know whether or not what you're looking at is a real stem cell treatment or misrepresentation? Here are some hints that can help you. It's a difficult field to navigate. The first, look at how many cell types per injury. We mentioned that cell types need to be very specific to replace damaged tissue. And one stem cell type cannot turn into cells of another. So it's very important. If someone's saying they're going to suck out one type of stem cell and use it for 12 different indications, it's likely something you should question. Second of all, you can check out their preclinical track record. Clinicaltrials.gov is a comprehensive database of all of the clinical trials if they want to get FDA approval. And the third and most important thing that you can do is to be knowledgeable. Do your research and get consensus. Ask your doctors, all of them, because they are here to help you. So, overall, stem cells have the potential to change life as we know it. Every single one of us is affected by diseases which stem cells could potentially help to treat in the future. And now that you have the knowledge, you have the power. It is up to you to spread the word about stem cells and to support reputable clinical trials. so that we can work hard to get the best treatments out to the people who need them the most in the shortest possible amount of time. Right now, there are many, more than ever before, treatments in the pipeline ready to come out. And the field of regenerative medicine is at critical mass. So I ask you to come join me on this journey. Come with me as newly minted purveyors of stem cell knowledge as we turn science fiction into science fact. Thank you.